Here's another class of problems that couldn't be solved without calculus: lengths of curves and areas and volumes. And you might think to yourself, well, I know how to calculate lengths, and I know how to calculate areas, and I know how to calculate volumes. And certainly you do. If you have 2 points, for example, you might need the distance between those 2 points in the xy plane, and you could find that with the distance formula. The distance formula basically just an example of the Pythagorean theorem. You find the x distance between the 2 points and the y distance between the 2 points, and you can draw a little right triangle, and the hypotenuse of that right triangle is the distance between those points. And that's pretty easy. Also, we can have basic shapes like a rectangle or a triangle, and it's pretty easy to calculate the area. The area could be the length times the width, or it might be 1/2 of the base times the height. Or there's certain three-dimensional shapes that we can calculate. A sphere, for example, a three-dimensional solid sphere, or a cylinder. Let's draw a cylinder like this. And there are known formulas for calculating the volume. The volume of the sphere is 4/3 pi r cubed. The volume of the cylinder is pi r squared h, and calculating those volumes is simply a matter of plugging the numbers into the equations. But there are many cases where we don't have straight lines or simple geometric shapes. There are plenty of cases, for example, where the line might be curved. Suppose we had this. Suppose we had, say, a cubic curve that looked something like this. And we need to find the length along the curve. So not just the distance between the 2 points, but we want to know actually how far you would travel if you moved along that curve from one point to another. That's an entirely different problem than just calculating the distance. Or suppose we had something like this. Suppose we had a parabola. Let's say we have a parabola opening downward here like this. And we're concerned about this area right in here. Okay, what's that area going to equal? Well, it's not a rectangle. It's not a triangle. It looks sort of like a triangle, but it's not exactly. This edge here is curved. So these formulas don't apply. We need some other formula or some other technique for finding that area. Or suppose we have a three-dimensional solid figure like this. Let's imagine taking a parabola and spinning it around the y-axis. So it generates this three-dimensional solid shape. And that's just one possible three-dimensional solid shape. But it's going to have a certain volume. What does the volume equal? We don't have a simple formula like we have for the sphere or the cylinder. We need a new technique or a new method for calculating those volumes. So for all three of these problems that I've drawn on the right, the simple formulas that we've learned, while they're certainly perfectly valid and useful formulas, the basic stuff we learned from pre-algebra up through pre-calculus, those formulas don't apply in these cases. And there are plenty of cases in the real world like these, where to solve the problem, we need calculus. And I'll go over one more modern example. This is dealing with rocket propulsion. And obviously they weren't dealing with this problem at the back of in the 1600s when they were developing calculus. But this is a great example of showing where the typical physics, the ordinary physics in math that we learn in high school doesn't quite work. Suppose we have a rocket. And rockets work by blasting their exhaust out the back. So this fiery explosion and all of this rocket exhaust comes blasting out the back, and as it gets blasted out the back, that creates a force that propels the rocket forward. And we know what applies here. The equation is F equals ma. So the rocket engine produces a certain amount of force, and that causes the rocket to accelerate. And we can very easily calculate the value for A based on the force and based on the mass of the rocket. If we know F, which we know how strong these rocket engines are, and we know M, which we know because we know the mass of the rocket because we presumably built it, then we can just put in those numbers and calculate A. But there's a problem. As soon as any fuel is burned, M changes, and that's the problem. So let's write that down. As soon as any fuel is burned, the mass changes. The fuel is part of the mass of the rocket, and as it blasts the fuel out the back, the mass of the rocket itself depletes. And if the mass changes, then the acceleration is going to change. And it doesn't just change for a little bit and then change again and then change again. It changes continuously. As long as the engine is burning, there's this smooth, continuous depletion of the mass. And so we can't calculate the acceleration. We can't just solve this for A and say A is equal to F over M. That would give us the acceleration at one particular moment, but as soon as it accelerates, mass has changed, and this value for A that we calculated has become obsolete. So we need a different method for finding the acceleration. The acceleration itself will be a function of time, and that's going to affect the velocity of the rocket and the distance it travels. Those will also be functions of time. And the simple equation F equals ma, or in this case A equals F over m, doesn't quite give us what we need. Another way to say this is that when the variables actually vary, the problems become problematic. So these variables don't simply have values, they have values that change over time. And when the variables actually vary, the problems become more problematic. All of these problems and many, many others can be solved using the techniques of calculus.